Good morning, how are you today? Hope you're feeling good. My name is Sara Benatmane, PhD student at the University of Science and Technology, Boumediene. Today I'm going to talk about a novel cryptosystem using an improved Diffie-Hellman by zero knowledge proof. I hope to add you some useful information on this subject, and if you have any questions, please don't be shy. On the screen, I have divided my presentation into three parts. In the first part, I will talk about the relationship between information theory and cryptography. In the second part, I will talk about modern cryptography, specialized in cryptography. And in the last part, I will show you our proposed algorithm. So, information theory and cryptography are two closely related fields that share a common goal: secure communication. Information theory deals with the quantification, storage, and communication of information, while cryptography is the science of secure communication. The relationship between these two fields can be understood in terms of the concept of secrecy and entropy. Entropy is a measure of uncertainty or randomness in the system, while secrecy is the degree to which information is kept hidden from unauthorized parties. Cryptography makes use of entropy to create secure communication systems by encoding information in a way that is difficult for an attacker to decode without access to a secret key. So what are the applications area related with information theory and cryptography? The applications area are many, as bioinformatics and genomics, deep space, machine-to-machine communication, Internet of Things, mobile communication, and digital banking. Many more. The applications are widespread. Again, these are some objectives of cryptography related to the privacy and secrecy. And the tools we use in cryptography are also a lot of pure math, computational complexity, probability and statistics, linguistics, perseverance, determination, and ingenuity. So at the heart of modern cryptography are two mathematical ideas. One is computational complexity, because given an infinite amount of time, you can make any cryptosystem, but that is not useful, right? We need to be methodologists. There isn't given an infinite amount of time. For that, we need analysis of algorithm, and we need to be know something about complexity of decryption algorithms and other decryption algorithms. And another important one is the idea of one-way function. The one-way function means given an input, it is computationally easy to compute an output. However, given an output, it is computationally difficult to find an input or the pre-image. So these are some examples for one-way function. We have two types of cryptosystem. One is symmetric encryption, where encryption key and decryption key are the same, and it must be secret. Also, so we pass to the Diffie-Hellman. The main idea behind the algorithm is to agree on a key that two parties can use for a symmetric encryption in such a way that an eavesdropper cannot obtain the key. It also depends on the difficulty to compute the discrete logarithm. Let me wrap up discrete logarithm. First, primitive root. Primitive root of a prime number n is number a, where a less than n and follow the below criteria gives a unique result for every a equal 1 to n minus 1 and I. For example, n equal 7 and a equal to 1 until 6. So this is the calculation. The primitive root is 3 and 5. Now discrete logarithm. If A is a primitive root of prime number P, then the number A modulo P until AP minus 1 modulo P are distinct and consist of the integer from 1 to P minus 1 in some permutation. Example, for any integer B and primitive root A of prime number P, we can find any exponent I such that this equation where I is between 0 and P minus 1. Exponent I is referred to as the discrete logarithm of B. This is an example. Now we pass to the algorithm of Diffie-Hellman. So we suppose sender A and receiver B. We note that sender A and receiver B. So A and B agree to on two large prime number P and G, such that G is the primitive root of P. Sender selects a random integer A where A less than P and compute FA. This is the public key, and receiver selects random integer B where B less than P and compute FB. And this is the public key for this is the public key. So sender send GA modulo P to receiver, and receiver send GB modulo P to sender. Receiver evaluate this quantity to be used as the K, and the sender evaluate this quantity to be used as the K. So now both parties have the common number. This is the symmetric key used by both sender and receiver. This works because through the other people know PG, GA modulo P and GB modulo P, but still they cannot evaluate the K because they do not know either A or B, the secret A and B. Now we pass to the modern cryptography, DNA cryptography. DNA cryptography is a new upcoming domain that is emerging based on DNA computing. It is the technology of bioscience to encrypt large message in compact volume. DNA cryptography is the process of securely hiding data in DNA sequence and using the Biot technology as a measure to convert plain text to ciphertext. Then the limitations faced by DNA cryptography are the need of biomolecular laboratories, requirements of huge computing time, high computational complexity. This is the definition of DNA. It is already well known. We pass to the problem statement. The need to enhance the performance and the efficiency of cryptographic algorithm made usage of DNA for secure the information and generating DNA cryptography. DNA cryptography field is difficult computation and its application is not fully understood, but using DNA sequences and forming proteins has engaged many scientists already. That's growing the subject for researchers in both biology and the cryptography. The traditional cryptographic systems are not enough due to the increases of security need and development of cryptanalytic procedure. Because of this reason, many researchers have hard work in providing a good and an efficient algorithm for cryptography. Now we are getting down to the heart of the matter. So we propose a new approach to symmetric key cryptography, consisting of two rounds of processing for delivering information security services such as authentication, integrity, and confidentiality. In the first round, we generate a secure seed by using a modified Diffie-Hellman by zero knowledge proof. After that, we generate a cryptographic secure pseudorandom number generator by C# and coded the K by the biological operation. In the second round of processing, the XOR arithmetic operation is used as an encryption technique. So this is an implementation. So we select one of the algorithm for coded the random number generator. Select DNA K or protein or mutation K. To that, that we generate the random seed by Diffie-Hellman modified by zero knowledge. Then this is the key generation. Then we coded the key generation by the biological operation of protein. We obtain a protein K. Then we verify NT, and after that, this is the encryption. This is the ciphertext. So this is the decryption. This is our message. We conclude, we propose an OTP DNA cryptography system with three algorithms for key generation for providing information security services, authentication, integrity, and confidentiality based on biological operation on DNA sequences, knowing that the key does not need to be repeated makes the process of selecting a key generation approach each time we want to do encryption a good addition to the one-time pad algorithm. It should be noted that biological operations take place in labs and that the suggested method is a simulation process utilizing a digital environment that cannot fulfill the necessary features in the biological environment, such as storage and speed, that take place in labs. The inclusion of zero knowledge proof protocol in the Diffie-Hellman algorithm makes our algorithm safer by generating a protein K, DNA K, and mutation K based on the user's plain text. The suggested approach makes cryptanalysis even more difficult. The purpose of utilizing a digital signature is to demonstrate message authenticity, integrity, and sender no repetition. Thank you for your attention.